Okay, hello everyone, and welcome to week 16 of Qubit by Qubit's Intro to Quantum Computing. Today we are talking about Qiskit. So this is kind of the first in a long series of labs coming up for pretty much the rest of the course, all about how to program quantum computers using Python, and specifically a library called Qiskit. So we had a bit of an introduction to the IBM quantum experience last week. Now we're going to be diving into what some of the code looks like, just getting our feet wet a little bit. But these are really sort of like the baseline fundamentals for pretty much everything that comes up after this, and which is really ultimately the point of this course, to teach you how to program quantum computers. So this is an exciting week. Let's go ahead and get started. Before we get into the lab content, just a quick plug for the Diversity in Quantum Computing conference that Qubit by Qubit is holding this weekend. So that is this Saturday, February the 27th. It is a 100% free, 100% virtual conference for high school students, young professionals, anyone who is passionate about making quantum computing the best place it can be in the future. You can go ahead and register at qubitbyqubit.org/conference. And of course, we definitely encourage all of you to go there if it is something that sounds interesting to you. It is completely optional. There's no obligation at all. You're not going to get marked on an attendance quiz or anything. This is just if you're interested and want to hear more. There's a number of interesting panels lined up. I would highly encourage you to check it out. Okay, so quick program, for today. We have one quick announcement. We'll do our attendance quiz, pre-lab Zoom feedback, one quick question from last week, and then for the main lab content today, we'll be back on the IBM quantum experience. The only difference is now instead of dragging and dropping to put together our circuits, we'll be coding in Python. And I'll show you how all that works when we get there. Okay, so quick reminder / announcement about Canvas announcements. This is something that hopefully you're already familiar with, but if not, here you go. There is an announcements tab on Canvas that you should be checking and sort of keeping up to date with every week. So that's where I personally post my follow-ups after these labs. So that includes the link to the recording as well as the slides and possibly other resources as well, depending on what we do. But the course staff also posts things there. So sort of admin reminders. We had the quantum experience instructions recently up there. Many more things. So this is a good sort of central communication hub to be familiar with. In case you had forgotten or weren't aware, that is where it can be found on Canvas. Okay, so let's go ahead and do our Canvas attendance quiz. Lab number 1, as always, the quiz password this week is 5267. So the question or questions, I guess, this week are a series of true or falses. And in contrast to previous weeks, these ones do have correct answers, right? Like all of them are sort of knowledge checks. But whether you get them correct on this quiz does not count toward your overall grade or anything. So just like past attendance quizzes, just answer the questions. And as long as you give some answer and fill out the quiz, you will be counted as present for the lab. We do want to start to get some sense of how students are grasping the basic concepts of quantum computing, though. So a lot of these questions, may or may not be things that we have directly said before, but we're hoping that you have enough knowledge under your belt at this point to be able to get, hopefully, the correct answers on these. But once again, don't worry if you don't get them correct. This is only for your attendance quiz. So just make sure you do fill it out. And I will also turn on the chat in case anybody has any issues with the Canvas attendance quiz. But once again, just to emphasize this point, even though there are correct answers to these questions, getting them correct has no bearing on your grade. Okay, so let's do the pre-lab Zoom feedback. Same question as always. I will pop this quiz up on your screen. Feel free to let me know what you thought about this week's lecture content. So as a quick reminder there on the bottom of the slide, in lecture this week, we introduced Qiskit, which is the Python programming framework for IBM's quantum computers. And we saw some simple examples of quantum circuits. So very similar to what we will be doing today and reviewing in today's lab. Okay, so I'll just give another 15 seconds or so. Somebody asks in the chat, will we see the correct answers for the attendance quiz? That's a good question. I'm actually not sure. If you don't see the correct answers, definitely well, I guess we can just let me know in chat here, and maybe I can go over them at the end of the lab session. No, you don't see the correct answers. Okay, yeah, if you want me to quickly mention them, maybe I'll do it toward the end. Okay, so I'm going to go ahead and end this poll so I can share the results with everyone, get a sense of where everyone else is at with the course. And with that, we will go ahead and launch into one question from last week before we get on with Qiskit for this week. So one of the things that we had a lot of questions on last week was, how does a CNOT gate work? Now, I believe it was in this lab section, but I did sort of an extra piece. I forget if it was in the required section or not, but I did give a bit of an explanation for why the CNOT gate works. I'm going to do a similar explanation here again, just in case you need a refresher or missed it last week. So a CNOT gate is different from what we've seen before because it's a 2-qubit gate. So everything we've seen up till now is a gate that only, you apply it to only a single qubit. A CNOT gate is applied to 2 qubits. Now, just like in the single qubit gates, one way that we like to talk about this is by describing how it affects the computational basis. So again, the computational basis is just all of the qubits that have zeros and ones in them. In the 1 qubit world, the only 2 computational basis states are ket 0 and ket 1. In the 2 qubit world, we actually have 4 of them. We have ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. Now, there's a couple things to note here. One, these are just all of the possible combinations of 2 qubits being 1s and 0s, right? So there's 4 of them. And if you remember back to way at the beginning of the course, when we talked about binary, you should also notice that the order I'm listing these in is counting up in binary, right? So this is 0, this is 1, this is 2, this is 3, counting in binary. This is just a convention that I'll usually follow. So in order to describe the CNOT gates, what I'm going to do is I'm going to try and work out what happens to each of these states when you apply the CNOT gate to it. Now, CNOT is short for controlled NOT, and it's actually part of a sort of family of gates that are what we call controlled gates. And how a controlled gate works is the following. We label the 2 qubits as the control and the target qubit. So this is a 2-qubit gate. We're going to give those 2 qubits names. One of them is the control, one of them is the target. So if the control is 1, then we're going to apply our gate, which in this case is the NOT gate or the X gate. And just as a refresher, what the X gate does is it just flips from 0 to 1 and from 1 to 0. Okay, what if the control bit is 0? Well, in that case, we do nothing. The gate has no effect whatsoever on our quantum state. So let's go ahead and apply that logic to our 4 computational basis states. In the first 2, you'll notice that the control, which is just the first qubit, the control is 0. And we said over here that if the control is 0, then we just do nothing. So these states just stay the exact same. Right? Do nothing. Now in the second 2, our control qubit is 1. What did we say when the control qubit is 1? Well, then we apply an X gate to the target qubit. So in this case, we're going to go from 1, 0, and this is going to turn into ket 1. Then the second qubit will be flipped because we apply the X gate. And then in the last example, again, we have ket 1, and then the second qubit is flipped because we applied an X gate. So that is how I like to think about how the CNOT gate works. You could write down a matrix representation for this, and there are sort of more formalisms that we'll get into later in the course with just how multi-qubit systems work. But this is one thing that it's fairly easy to explain logically, as I've done here. And so we'll see one more example of this today as well, how it works in a regular circuit. So any questions on this? Okay, so there's a lot of stuff in the chat. Okay, so one person asks, what lecture can I review to understand Bell states in regard to phi and psi? Can you cover this today? Yes, I can, absolutely. We're going to be talking more about the Bell states when we get to our Qiskit notebook. So just hold tight on that. Okay, Bell states. Everyone should have gotten full marks on that quiz, even if you didn't get the correct answers. So I will go over the correct answers toward the end of the lab, but you should have all gotten full marks just for being marked present on the quiz. That is my understanding as well. Okay, good. So everybody is sharing the notebook link. Okay, I'll go over how to do this as well, just in case you're confused. Please note, Corbin. What do I note? Okay. Let's see. So somebody else asking about the circuit builder. So we're not going to be talking about the circuit builder today, but if you are running into any issues with that, try watching last week's lab, I guess. If there's any sort of pointers you can get from that on setting it up, that's where I went over the circuit builder. If not, though, I would recommend either posting on Piazza or going to one of the sort of like office hour help sessions on Fridays to possibly try and troubleshoot that. Oh, interesting. Oh, I see what this person is saying now. So one person asked, why is there not an upside down CNOT in the IBM quantum experience? That is a good question. So, I mean, you can certainly have an upside down CNOT. Now, what I think you mean by upside down CNOT is just where instead of the first qubit being the control and the second being the target, you would have the first qubit being the target and the second qubit being the control, right? Something like that. You can totally have that. I guess sort of the default is to have your target as the second qubit, your control as the first qubit, and that's how it's written in the IBM quantum experience. There is a way to swap it though. I didn't go over it last time. It's just a different setting on the user interface. So there is an option for it. It's totally allowed. It's just not the default, is the short answer. So one person asked to just go over the CNOT gate one more time. So I think the most important sort of pieces to get out of this explanation are the following. So first up, we can construct what is kind of like a truth table, right? So remember before in our binary, when we learned about binary, we would often construct truth tables. This is pretty much the same thing, right? You can think of this as a truth table where you have two qubits, right? Q0 and Q1. And then you are going to apply the CNOT gate in the middle here, and then you're going to get some CNOT of Q0, Q1 on the other side. That's effectively what we've done here. So on the left, we wrote down all combinations of 2 zeros and 1s, just like we did in the binary section. And then on the right-hand side, we used our logic over here, looking, I guess I'll write explicitly. The left here is the control, and the right qubit is the target. So we just use this logic. It's easiest to start off if the control is 0, we just do nothing. So on these first two states, the control, the left qubit, is 0. So we just do nothing. Those states remain the same. In the second two, the control is 1. So again, you're looking at the first qubit is 1. Therefore, we are going to apply the X gate to the second qubit, the target. And so what you'll see is here we go from 1, 0 to 1, 1. And then on the bottom, we go from 1, 1 to 1, 0. So the control qubit stays the same. The target gets flipped because this is a controlled X gate. Hopefully that helps clear it up a little bit. Okay, to the person who asked about matrix multiplication for CNOT, we will be getting into this later in the course. Resources off the top of my head, I'm not really sure, to be honest. But it is a fairly simple extension to what we've learned, and we will be going into it later in the course. Okay, let me see. Oh yeah, sorry. So somebody said, I wasn't able to attend the week 16 lecture. Will I understand today's lab? That's my goal. So hopefully you'll be fine, but definitely feel free to ask questions if you do get confused on anything. Okay, so let's go ahead and go to this week's lab content. I will show you how to upload a notebook. So just hold tight on that. All of today is basically about Qiskit, right? So how we use Jupyter notebooks on the IBM Quantum experience, how we sort of import and start using Qiskit, and then we're going to do some sample circuits using the Qiskit programming framework. So defining qubits, applying gates, visualizing the results, and then finally, we'll end off with an example doing the entanglement circuit from last week, so the one that had the Hadamard and the CNOT gate. We'll do that same entanglement circuit in Qiskit, just so you can start to see some of the similarities and differences between the circuit builder and Qiskit as a framework. Okay, so let's go ahead and get started. This is a slide we saw last week. I just wanted to sort of really quickly review it because we will see similar concepts coming up in Qiskit. A quantum circuit generally has three parts. There's going to be your inputs, which are your qubits that are being fed into the circuit. They are initialized in some way. And when we say that they're initialized, we just mean that they start in some specific state. So in this case, all of our qubits are initialized as ket0, which just means they all start as ket0. Next up is going to be the gates. So our gates are applied sort of in order from left to right. Right? So here we apply a Hadamard on the first qubit, an X gate on the third, and then we have two CNOT gates. So from last week, again, this sort of symbol with the filled in dot and then the cross is the symbol for a CNOT gate. So you have all your gates in the middle, and then the final step in quantum computing is measurement. That's a step that always exists in classical computing as well. It's just we don't usually think about it because measurement in the classical world is very straightforward. In the quantum world, it's not as straightforward. And so we do have to think a little bit about how measurement should work. So as a reminder, in the IBM quantum experience, so both the circuit builder and with Qiskit, your states are always initialized to 0. So we're going to tell it how many qubits we want, but we're not going to have to tell it which state we want them initialized in. It'll just default to ket0, which 95% of the time is what we want. So we're not going to focus too much on that. We'll more be looking at the last two here, the gates and the measurement and how you do that in Qiskit. Okay, so without further ado, let me go ahead and switch screens over to the IBM Quantum experience. And I'll show you how to navigate to the Jupyter notebooks. I'll show you how to upload, and then we'll go ahead and get started. Okay. Okay, so hopefully everyone can see my screen here. Now, let me just reset to what you would see if you first log in. So this is the screen that you would see if you first log into the IBM Quantum experience. This is also the screen that we saw last week when we were just starting off. Now, last week we went over to the circuit composer on this. Oh, actually, I just remembered too. I should enlarge this a little bit. So is this good for everyone as far as just scale to see everything? Yes. Okay, cool. Okay, so yes, starting off from the home screen. Oh, one more person says Zoom. Okay. So starting off from the home screen, I am going to go over to this left-hand menu. Now, last week we went to the circuit composer, which is right here. Instead, we are now going to go to the quantum lab, which is just the next one down. So I'll go ahead and click that, and we get to the quantum lab. This page might take a little while to load if it's your first time coming here. Don't worry about that. It should work in the end. The first thing you'll see is a number of Qiskit tutorials. So these are not Qubit by Qubit. These are provided by IBM. If you're curious, you are of course welcome to look through these. So, you've got quantum chemistry, quantum circuits, advanced quantum circuits, finance, machine learning, et cetera, et cetera. All of these are things you can do on quantum computers. Most of them will be more advanced than what we've seen so far. But the hope is that at least by the end of this course, you should be able to start making your way through some of this content. If you're curious now, though, feel free to take a look at what some of IBM provides. What we're going to do today, though, is scroll further down on this page to where our notebooks live. So down here is all of our custom notebooks. Now, what you should do with the notebook that you downloaded is to import it. So you would just click this import button. It'll bring up a file selection screen, and then you just select the IPNB file that you downloaded from Canvas. Once you do that, you should have your notebook appear here. So it was called the Q by Q Basic Qiskit Introduction Lab.ipnb. So once you import it, it should appear here, and you can go ahead and click on it to open it up. Okay, so it's going to take a little while to load. Totally normal. There's quite a bit of stuff happening in this notebook, so we'll just give it some time. Let me see if there's any other questions. I don't think so. Oh, one person asked, is it okay to run these notebooks locally? So what they're saying here is, I'm going to be demonstrating everything on IBM Quantum Experience's website. If you are familiar with Python and Jupyter, you might know that you can also run these notebooks on a local application on your computer. Totally fine. I would say that the setup is probably going to be easier on the Quantum Experience. If you can figure out how to set it up on your computer, that's totally fine though. Like everything can still work on your computer. We're just using the IBM Quantum Experience because it does a lot of the setup for you. Yes, I will talk about the different simulators. Great questions. Okay, so quick overview then of what we're going to be going over today. We'll have an introduction and then basically the sections I went over before. We'll talk about how to import Qiskit, so how you sort of enable Qiskit within your project. We'll talk about building quantum circuits. We'll talk about visualizing quantum circuits, adding gates, and then finally, we'll do a simulation example with the entanglement circuit that we saw last week. Now, before I get too far into this, well, let me just do a quick overview, I guess, of Jupyter. We haven't seen a Jupyter notebook before. So this file that we have, this IPNB file, is just like any kind of file. It's like a Word doc or a PNG file. But these particular files are called Jupyter notebooks. And the way to think of them is they are really just like a notebook, right? So as you can see here, you can put text in it, you can put links, you can put headings, you can put, you can bold things, all of that. But what makes Jupyter notebooks special is you can also put code in them. And we'll see the examples of that later on. You can put code in Jupyter notebooks and you can run code too. So it's kind of like a combination of a regular note-taking app plus a programming environment. So it's really, really powerful for communicating ideas and programming. And you'll see that we're going to use them for pretty much the rest of the course because they are super helpful. Now, the general layout of a Jupyter notebook, it's going to be divided into what we call cells. Okay, so each of these sort of white backgrounded areas are called cells. So for example, this top one here is a header cell. Then we have our table of contents cell, and so on and so on. And you can move between the different cells just by selecting them, by clicking them. So you'll see the little blue line flipping back and forth as I click between the cells. Now, one last note I will make on these notebooks is there is a lot of text in here, right? So we've written down a lot of what I'll be talking about in text because when you have this notebook, we hope that you'll be able to go back to it for some notes on your own, right? So even if you forget what I've said, or if you need a review, of course, you can go back and watch this lab, but you should also be able to get everything you need just by reading what's in these notebooks. So I am not going to read through everything. I'm going to kind of skip over a lot of the text. I'm going to ask you all to try not to read it now as well, like try and actually listen to what I'm saying instead of reading. I will repeat everything that's in these text boxes that I think is important. So don't worry about trying to read it right now. I will be saying everything out loud as part of the lab. Okay, so let me just quickly look at what's going on in the chat. Okay, so let me see. So for the person who asked a question about the week 16 homework, I guess they asked if anybody else is having this problem. If you still can't figure it out, feel free to post on Piazza, right? I won't get into the specifics of homework questions here, but definitely feel free to post on Piazza if you're still running into problems. Okay, so a few people saying they're unable to locate the IPython notebook in Canvas. Interesting. So I think, yeah, okay, somebody sent a link to the file. Good, all right. Someone can't see the text on their notebook. So if you're running into technical issues with getting the Quantum Experience notebook running and seeing what I'm seeing here, I'm not going to try and live troubleshoot individual students here, but do feel free to post on Piazza or to go to one of those Friday review sessions, and hopefully we can get you fixed up. For the time being, if you cannot do it on your own computer, feel free to just follow along with my screen share because I'll be doing everything here as well. Oh, okay. Apparently the file name is a bit different. That could be the case. Okay, cool. So I think I'm good to go. Once again, if you're having troubles getting the notebook open like this, don't worry. There are ways to fix that. I just won't do it in this lab. So feel free to just follow along with the screen share. Okay, so let's get started then with a quick introduction. Now, I'll talk briefly again about what exactly Qiskit is. So a few labs ago, we introduced you to Python and we talked about what libraries are, right? And in my opinion, and the example that we used in that lab, the best way to think about what libraries are is it's kind of like, you know, if you have a smartphone and you have apps on your smartphone. So in this case, Python is kind of like the smartphone itself, right? Python is the base, the foundation that enables you to use all of these other apps. The smartphone provides some functionality on its own. So for example, your phone would have a calculator on it. It would be able to phone people and text people, probably even browse the internet, all that kind of thing. But if you wanted to do anything more specific, more specialized, then you would have to download an app from the App Store. It's pretty much the same idea with Python. The language Python provides you with a whole bunch of reasonable defaults. You know, you can do basic math, you can print things to the screen. But if you want to do something specialized, like quantum computing is certainly specialized, then you need to add a library. And the library we're going to use is called Qiskit. That is what IBM provides to do quantum computing. Okay, so this little block of text here just talks about Jupyter notebooks and cells. I already went over that. And then here we provide just a table of some useful commands that you can use in a Jupyter notebook. Now, I'm not going to go over all of these. And in fact, I personally, during these labs, I'm going to try not to use keyboard shortcuts too much, because I know that you watching the screen share can't tell what keys I'm pressing. And so it can easily get quite confusing with what's going on. I'm going to do my best to just use the buttons on the interface here. So if you want to use the keyboard shortcuts, go for it. You can learn them. You can probably become a lot faster if you use the keyboard shortcuts, but no obligation whatsoever. I'll show you how to do everything just using clickable elements on the screen, so you don't have to use the shortcuts if you don't want. Okay, so the first topic is importing Qiskit. So this is a little bit of code you'll see at the beginning of every notebook, pretty much. And all it's going to do is sort of tell the notebook that we intend to use Qiskit. So just like on your phone, how you need to go to the App Store and download a new app before you can start using it, in Python, you have to import a new library before you can start using it. It's the same idea. So I'm not going to go over this in too much detail. We will always give you these statements, so you don't have to know them or understand them or figure them out. But I guess I will talk a little bit about what each of these elements does as we get to them. In particular, two that are important are things called tera and air. So tera is just spelled like this. Air is A-E-R. Okay. So the first one, yes, tera. So tera is sort of the basic piece of Qiskit that provides all of the building blocks necessary to create quantum circuits. So it's going to let us, add new qubits. It's going to let us put gates on our qubits, all that kind of stuff. So if you ever see tera referenced, that's just the foundational quantum computing library used in Qiskit. Air, on the other hand, Air, on the other hand, is what provides high performance quantum computing simulators. So for all of this lab, we're just going to be using simulators to run things. Air is actually a family of simulators. There's a bunch of different simulators within Air. We're going to talk about a few of them today, just so you can get a sense of what kinds of things are in there. So again, just to summarize, Tera lets you build quantum circuits by adding quantum gates to qubits. Air is going to provide you with a whole bunch of different simulators to choose from to actually try simulating your circuit and seeing what happens. Hopefully this will become more clear as we actually do some practical examples. So let's go back to this cell, this Jupyter Notebook cell that has the code in it. Now, the thing with Jupyter Notebooks is you have to manually run all of the code in the notebook. So I'm just going to select this cell. Again, you can select it by clicking on it. And then I'm going to go to the top part of my screen here and click the run button. So if I just click this, it was very fast there, but the little number inside these square brackets turned into a star, like an asterisk. That means that the cell is running. And then once it turns back into a number, so here it's a 5, that means it's done running. So this cell, it ran, it imported Qiskit for us, and now it is complete. So once again, just to show how that works, you click your cell to make sure it's selected, and then I'm going to click the run button, and you'll see this number in the square brackets, it'll turn into an asterisk while it's running, and then once it turns into a number again, it means it's done. So I'll go ahead, click run. It really quickly turned into an asterisk, and now the number has updated to show us that the cell has been run. So that's the basic sort of workflow of a Jupyter Notebook cell. You type in some code, you click it, you hit run, and it'll execute the Python code for you. Okay, so next up, we're going to do just a quick check and another sort of practice, I guess, on executing cells in the notebook. So one of the commands that we imported is called Qiskit version, and it has these 2 underscores before and after it. Now, this is a command that you can run to see, well, as you can tell, what version of Qiskit you are currently running. So in order to try this, I'm going to give myself a new code block, a new code cell. So to do that, again, I'm just going to go up to the top of my screen here and hit the plus button. So the plus is going to give me a new code block right below where I selected. So in this code block, I can click and I can start typing code here. So this is just regular Python code. I could print hello world, and that would run just like regular Python code. Just to show you, with this cell selected, I'll go ahead and click the run button, and we'll see that it prints out hello world, just as expected. Now for this, we actually want to see Qiskit version. So in order to see our Qiskit version, all we have to do is actually type in Qiskit version, no prints, no nothing else. We'll just put that in our cell, and then I'll go ahead and click run. Okay, so now as output, it's given us a few different version numbers. First up is Tera and Air, which are the 2 that I described earlier. And you can see that those are version 0.16.4 and version 0.7.4. So this doesn't really mean anything to us. It's more just here so you can check and verify that you're running the same versions that we are as I'm teaching, for example. Okay, so before we go and build our first quantum circuit, I'm just going to take a sec to go to the chat and see what's going on there. Okay, So yeah, thank you to everyone providing the extra links and everything. I didn't realize that the file name was going to be different. I do apologize for that. It seems that it's called lab16.ipynb. So go ahead and download that, and then you should be able to import it. Yeah, so one person asks, what is this sort of, if I go to one of my code cells, what does it mean when it says in and then the little number in brackets? You don't have to know exactly what those numbers mean. The most important thing to understand is that when it's a star, it means the code is running, and when it's a number, it means it's finished. So you can just think of it as an indicator of whether your code is running. Okay, so I think that's it as far as questions. Did anybody else have questions so far about sort of adding a cell, typing code into the cell and running it? Or does that seem straightforward so far? Okay, I know that there's a lot of new content in this, so feel free to stop me if you do have any questions about what I'm doing. Okay, cool. So why don't we move on and start building our first quantum circuit? Okay, so the most important command for building a quantum circuit is, unsurprisingly, the quantum circuit command. So it's the Q and the C are capitalized, and it's all just in one word. Now, this is actually, it's going to look kind of like a function. So when we create a quantum circuit, we're going to have to give it an argument, just like when we had a function. What were some of the ones? We had like a function called like print hello or something. Okay, sorry about that. I think that my internet just died, maybe, or something else. I'm not sure. Hopefully I'm back now. Hi. Okay, let me reshare my screen. Hopefully nothing broke there. Sorry about that. To be honest, in some ways, I'm kind of surprised that, we haven't had more technical issues with the whole online school thing. But anyway, hopefully that doesn't happen again. So what was I saying? Quantum circuits, yes. So this quantum circuit command is what we're going to use to build a quantum circuit. And we're just going to give it one argument, which is the number of qubits. So remember before I said we don't have to worry about initializing our qubits. Qiskit is going to do that for us. It's going to initialize everything to ket 0. But we do have to tell it how many qubits we want in our circuit. So let me go ahead and add another code cell here. So again, I'll just select the plus button. It's going to give me a new code block. And I'm going to create a new quantum circuit. Now, the way I'll do this is I'm going to assign it to a variable. So remember the way that we create variables in Python, we just have some var name equals 2, right? And that would make us a variable called var name that has value 2. In this case, I'm going to call my variable circ, just short form for circuit. And then to create our quantum circuit, we're going to use that quantum circuit command. And then remember to pass arguments. We do brackets, and then I'm going to tell it how many qubits I want. So here, I'm going to say I want 1 qubit, for example. Okay, so I will go ahead and click run on this cell. Now you can see that we have a number in the square brackets, which means our cell ran. It didn't give us any output, like there's nothing printed here, but that's okay. We didn't try and print anything. We just created a new variable. So I think this seems to have worked. Now, as just a reminder here, all of our qubits start off in the state ket 0 by default. And just a final note that there's nothing special about the name circ here. I could have called it circuit. That's no problem. I hit run, and now my variable is going to be called circuit instead of circ. Name it whatever you want. As long as you're consistent throughout your Python notebook, everything should work just fine. Okay, so I'm just going to check the chat real quick. Okay, yeah, sorry, everyone was. No, you didn't freeze. That was me. Okay. What is the argument 1 in the code? Yeah, so that's the number of qubits, exactly. Okay, yeah, and I'm not going to go into more detail on what this underscore underscore meant on the Qiskit version. If you want to, you can look into it more. But for our purposes, you just need to know that typing this into a code block in your notebook will give you all the version numbers to verify that you're running the same versions that we are. Okay, cool. So that was the first step, building a quantum circuit. Now we have a variable called, in this case, circuit. I guess I'll change it back to circ, just so it's consistent with the notebook that you all have. So I have a variable called circ. It's a quantum circuit, and it has 1 qubit that, as a reminder, is initialized to the ket0 state, just as a refresher. Okay, so next up then is we've created this circuit. How do we visualize it? How do we see what we've actually done? Now, it turns out there's a lot of different ways that Qiskit can do this. All of them, though, are going to involve this draw function. So quantum circuit.draw is what we're going to be using to draw our circuit. So I'm going to go ahead and give myself a new cell to code something again. And I'm just going to try this. So what I'm going to do is I'm going to do my name of my quantum circuit variable. So in this case, that's circ. And then we just do .draw at the end of it. Okay, now this is the basic command to draw a circuit. We have to tell it what method we want it to use to draw our circuit, though. Now you can see some of those are mentioned here. We can print it using text, LaTeX, LaTeX source. There's a bunch of other ones as well. Don't worry if you don't know what some of those are, that's okay. We're going to use one called matplotlib, which is a bit of a tongue twister, but it's MPL for short. So in my circ.draw function, I'm going to pass it a string that says just MPL, which again is short for matplotlib. And this is telling Qiskit how we want to draw our circuit. So we've defined our circuit. It has 1 qubit. We want to draw our circuit, and then we're telling it how we want to draw it. So let's go ahead and hit run on this. Okay, and we see we get an output, right? This Q here is our first qubit. We haven't done anything to any of our qubits yet, so this should make sense. I can go ahead and try something else here. So for example, if I want to draw it in text form, I can write text here, click run, and you'll see that now it just gives me some simple text output. But it's the same idea. It's always going to draw our quantum circuit using some method, using text, using matplotlib. It's up to you. We'll use matplotlib for most of these labs just because it gives you a nice visual representation. Okay, what else do I want to say here? I guess the only other thing I'll mention is just to drive home that this is actually drawing our circuit. If I go back up to where I defined my quantum circuit, and instead I make it, I don't know, say a 3 qubit circuit, right? If I run this cell, that's going to update my circ variable to now be a 3 qubit circuit. So if I scroll back down to my visualization, you'll note that it has not updated, right? Our visualization still only has 1 qubit. That's because in Jupyter notebooks, you have to explicitly tell it to run a code block in order for it to update. So here, if I want to see the updated picture, I need to select this code block, click run. And now you'll see that it's drawn 3 qubits for us, right? Again, we haven't done anything to these qubits yet, but this is indeed drawing our circuit, which we've called circ. Okay, so I'm just going to go back and change this to a 1 qubit circuit, just so it's all consistent with what we've seen. So we have just a single qubit. All right. So that is the end of that section. Now we go on to adding gates to our circuit. Now, just like last week, we're going to use this example of an entangling Bell state, is what we call it. So here are 4 definitions of the standard Bell states. Now, why these are called phi plus, phi minus, psi plus, psi minus, beyond the scope of what I'm talking about here. But you can just sort of take these definitions as givens, right? Just take as a given that we have this state called phi plus, and it is equal to this superposition. And then there's these 3 other ones as well. These are collectively known as the Bell states. So if you hear us referring to that, this is what we're talking about. Now, in last week's lab, we used the circuit composer to build the first Bell state, which is phi plus. And we're going to do the same thing in this week's lab as well, but of course, using Qiskit. Before we get into that, though, I wanted to talk a little bit about state vectors. So this is something that you have seen, this is something you have seen already in the 1-qubit world. So state vector, scary sounding word, but really not something new for us. So as we have seen, you can draw quantum states using a form like this, right? You could have ket psi equals ket 0 plus ket 1 over root 2. That gives you a 50-50 superposition. Now, we learned that this bra-ket notation, sometimes also called Dirac notation, is really just a short form for linear algebra, right? So an equivalent way of writing this quantum state would be to write it as a vector, 1 over root 2, and then a vector with the ket 0 element on top and the ket 1 element on the bottom. That vector is generally called a state vector, right? So we've seen state vectors before. Literally all it means is a vector representing a quantum state. Once we get into the world of 2 qubits, things change a little bit, but it's still very similar. So as I pointed out when I was describing the CNOT gate, the computational basis for 2 qubits is now 4 elements large, right? We have 0, 0, 0, 1, 1, 0, and 1, 1 as our 4 basis elements. So when you draw a state vector for a 2-qubit system, you are now going to have a 4-dimensional vector. So you can see an example of that right here where I'm moving my mouse. It works in the same way as with 1 qubit. The first element is the coefficient of your ket 0, 0. The second element is the coefficient of your ket 0, 1. Third element is your ket 1, 0. And the fourth element is your ket 1, 1. So this equation right here is saying the exact same thing as this state vector over here. Now, the reason that I'm talking so much about state vectors is because Qiskit tends to use state vectors as its sort of language of communication, right? So whenever we get it to print out a quantum state, we're going to see the state vector. It's not going to explicitly tell you what all of these basis states are. It just expects you to know that if you get a 4-dimensional state vector, that is 0, 0, 0, 1, 1, 0, and 1, 1. So that's just kind of something that you have to memorize. Okay, so with that covered, let's return to the idea of Bell states and how we might construct one. So last week, we already saw the circuit for this. The way it works, as a refresher, is we apply a Hadamard gate on qubit 0, which puts the first qubit into a superposition state, 0 plus 1. And then we do a controlled NOT, or a CX operation, between qubits 0 and 1. And then that will should give us the first Bell state. Now, again, both last week and this week, we're going over this circuit pretty quickly. I believe last week I went into a bit more detail on how it works, but as far as the course is concerned, we're going to go into a lot more detail on 2-qubit circuits very soon. So we're mostly just using this as an illustrative example. Don't worry too much if the exact workings of the circuit don't make sense yet. Okay, so actually, I forgot to clear this out. It's my bad. Okay. So we're going to go ahead and write this out then. Now, the first thing that I'll do is I will create a quantum circuit. So this is a new one that we'll call the Bell circuit, for example, and we'll create it as a quantum circuit now with 2 qubits. So just as a reminder, this is referring to the number of qubits in our circuit. Okay, so next up, I want to apply a Hadamard gate to the first qubit, right? So the way that you apply any gates in Qiskit is by starting off with the circuit name. So I'm going to start with circ Bell. Oops. Circ Bell. And then you do a dot. So just like we did dot draw to draw our circuit, if we want to add a gate to our circuit, we do dot and then the gate's name. So in this case, I want an H gate. So I'm going to do circ Bell dot H. And this is also going to take an argument because, we've told this thing that we want an H gate in our circuit, but our circuit has 2 qubits, right? So do we want our H gate on the zeroth qubit or the first qubit, right? Remember, in programming, everything is 0 indexed. For us, we want our H gate on the first qubit. So I'm going to pass this index 0 to indicate that the H gate goes on the 0th qubit. So that's all you need to do to add an H gate. That command, that circbell.h, and then giving it the qubit number, that is the exact same as sort of dragging the H gate onto our circuit in the circuit composer, except now we're doing it in code. Okay, so next up then is the CX operation between qubit 0 and qubit 1. Same exact idea. I start off with the circuit name, circbell, then I do a dot and the gate name, CX. Again, I need to tell it which qubits I'm applying my gate to. In this case, CX is a 2-qubit gate, so I have to tell it what the control qubit is and what the target qubit is. So there's 2 sort of qubits that we have to name. So in this case, the control should be the 0th qubit, and the target should be the first qubit, right? So that's, again, the same as dragging and dropping our CNOT gate onto our circuit. The top qubit was the control, the bottom qubit was the target. This is what that looks like in code. Okay, and then for a final step, I will go ahead and draw this circuit. So again, we start with the circuit name. You'll notice this is a very familiar trend. Most things in Qiskit start with the circuit name. And then we do dot draw again, and I'll use matplotlib, just like that. Okay, so if I go ahead and click run, we should get the same picture that I had before. So here we have our 2-qubit circuit. We've put an H gate on the first qubit, and then we put a CNOT with the control as qubit 0 and the target as qubit 1. So this is exactly what we're expecting. Okay, so I'm going to go ahead and put up a Zoom poll now. We actually have 3 questions. Let me see if I can get them all on the screen. There we go. Okay, so these are just a couple of questions to test your understanding of what our various commands do. So I actually created these as 3 separate Zoom polls, which in hindsight was kind of silly. So we'll start with the first question. In circbell equals quantum circuit 2, what does the 2 represent? So I will give not too long, maybe just like 45 seconds or so for everyone to answer that question, and then we'll move on. Okay, so about 2/3 of you have voted. I'm going to go ahead and end that. The correct answer here is the number of qubits. That was B. 2 in this quantum circuit means that there are 2 qubits in our circuit. Okay, let's go on to the second one then. In circbell.h and then 0, what does the H represent in this statement? So again, or sorry, what does the 0 represent? My bad, I can't read. So again, one of the confusions with Qiskit oftentimes is that there's a lot of these sort of random numbers floating around. So we just want to make sure that you're clear on what all of these numbers mean in these contexts. Okay, let me just see. I'm looking at the chat. So somebody asked about finding the video recordings for all previous labs. All of those should be on Canvas. So in the sort of like course content, I'm not exactly sure what it's called, but in the course content screen, you should be able to scroll down to any week and find that week's recordings there. So somebody asked me in a direct message, how did you decide that for ket 00, you get half and for the remaining all? I'm not exactly sure what that question means. So if you could rephrase, I will try and address it. How can we create a W state? I will not be going over that here, but maybe I can do it in the optional content. I will make a note for that. Again, totally optional. You don't have to know what a W state is. Somebody asked how we can apply something to multiple qubits at the same time. Yeah, good question. So actually, well, I'll put up the final quiz. Sorry, we've had enough people answering this. So going back to the question, in circbell.h of 0, what does the 0 represent? The correct answer here should have been the qubit on which the H gate is applied. So that was answer B. A few other people said that it was the initial state of the qubit. Again, the initial state is always 0. We don't have to tell Qiskit that. So what the 0 means here is indeed that we're applying the H gate to the 0th or first qubit. Okay, so let's go on to the third question here. In circbell.cx01, what does the 0 and the 1 represent? So while people are answering that, let me address the question of how to apply multiple gates at the same time. So I'm assuming what you mean by this is, for example, in this circuit, if we wanted to apply an H gate to both of the qubits at the same time. In Qiskit, there's no way to sort of explicitly tell it to do two things at the same time. But instead, what I can do is I can just tell it to first apply an H gate to the 0th qubit, then apply an H gate to the first qubit, like this. And if I click run, you'll notice that there's not a distinction between which of these H gates happens first, right? Qiskit is smart enough to know that they don't affect each other, and so it can just run them at the same time. Okay. Cool. Okay, so the final piece, oh, actually, we're almost out of time on this lab. I apologize for that. I'll probably go about 5 minutes over talking about visualization. Okay, so the answer to this question, this concept question of the control X with 0 and 1, the correct answer to that should have been the first, the control qubit and the target qubit of the CNOT respectively. So this is another point of confusion where you sometimes confuse which is the target, which is the control. It always goes control, then target. So the correct answer there should have been A. Okay, so final piece then is on simulating gates. So this is where we get to one of the questions that someone asked earlier about the various simulators available in AIR. So as I said before, Qiskit AIR is just a family of a variety of simulators that you can use. The three that I'll mention here are sort of the most popular ones. The first one is the QASM simulator. So that is what we saw last week when we were executing things in the circuit composer. It is going to simulate your circuit, and it's also going to try and simulate some of the quantum randomness, right? So to use the QASM simulator, you need to tell it how many shots you want, right? So before we had 1,024 shots, which just meant executing our circuit 1,024 times. And it's kind of like flipping a coin 1,024 times. You might not get exactly 50-50 heads and tails, right? There's a little bit of noise and randomness in that simulation. The second option is the state vector simulator. So what the state vector simulator does is essentially just linear algebra. It lets you put together your state, and then it's going to compute, given an initial state, which, as we say, is 95% of the time going to be all zeros. Given all zeros and your circuit, what's going to be the output? So it's just going to carry out a whole bunch of linear algebra and spit out what that output state should be. This is the one that we're going to use in this lab, so more to come on that in a minute. The third one that I'll just mention, which we have not really seen before, is called the unitary simulator. It's a very similar idea to the state vector simulator, except now it's going to compute the matrix for the circuit that you define. So instead of telling you, given this initial state, do all of these gates on it, what's the output? The unitary simulator doesn't care about the initial state at all. It just cares about the gates. And it basically does matrix multiplication to figure out what the matrix representing the whole circuit should be. Okay, so as I said, we'll just focus on the first two because those are the ones we've seen. I'm going to use the state vector simulator here. So again, to select a particular simulator, we're going to use the following syntax. So we're going to create a variable called the backend. I should mention, by the way, all of these different simulators in the terminology of AIR are called backends. So, there's a QASM simulator backend, a state vector simulator backend, a unitary simulator backend, so on and so on. We're going to create a variable called backend that holds the one we want to use. And so to get the one we want to use, we're going to use air.getBackend and then pass it the name of the one we want. So here we want state vector simulator. You could also pass in QASM simulator to use that instead. But what we're going to show here is the state vector simulator. So I'm going to go ahead and run this. We change to a number, which means we're all good to go. Okay, so I already talked a little bit about what the state vector simulator does. So next up, we need to run our circuit somehow, right? So in the circuit composer that we saw last week, this was the big blue button in the top right? And it was, run on QASM simulator. We need some kind of equivalent for that in Qiskit. And the equivalent is going to be this execute function. So we're going to call execute, and the two arguments you pass to it are the circuit you want to execute and the backend you want to use to execute it. Now we're going to save the result of that to a variable called job, because just like in the circuit composer, when you run execute, it doesn't immediately do your computation. It actually puts it into a queue, right? So just like we saw on the simulator, on the circuit composer, it's going to put it in a queue, and you might have to wait a little bit of time to see, what your results are and to let your job actually be run. So this little job variable is going to let us see the status of our job as well as see the results of our job once it's done. Okay, so I'm going to go ahead and run this statement. So as soon as this statement completes, our job has been sent off to the simulator and it's going to start running. So by the time we actually try and look at the results, it should already be done. In the meantime, let's do one last quick Zoom poll here. So I'll pop up the poll on your screen. And the question is, in the above statement with job equals execute, circbel, and backend, what are the inputs to the execute function? And here, again, you can select more than one answer. And by the way, I will remark, it seems like a lot of people are getting these correct, which is awesome. I guess the reason that we have them is just because it is a constant source of confusion for people what the arguments to all these different functions mean. So if the best way for you to remember that is just to go back to these notebooks, we've written down what all the arguments mean. That's perfect. Use whatever method works for you to try and remember what all these various, execute, if you do .hgate, what the arguments mean, all that kind of stuff. Just try and keep that straight in your head as we go through the course. Okay, so let me continue here. So the answer to this question, about 2/3 of you have voted. It should be that the inputs to the execute function are circbel and the backend, which again are just the circuit you want to execute and the backend you want to use to execute it. Cool, okay. So now all that we have left is to try and look at the results of our simulation. So the first thing that we can do is get the result. So in order to get the result, we're going to use job.result and assign it to a variable here called result. Nothing too complicated there. Remember, job is the variable that we got from executing our circuit. So we've executed it. Now we want to get the result, and we're going to save that in a variable so that we can inspect it later on. So I'm going to go ahead and run this command. Okay, and now there's two ways that we can look, actually 3 ways, sorry, that we'll go over, that we can look at the results. The first one is to look at the state vector. So again, the state vector is that vector representation of our quantum state. And in order to do that, we're just going to print out result.getStateVector. So this is the Qiskit command to get the state vector from your result. As a reminder, what our execution or our simulation was in the first place was starting off with all zeros, run our quantum circuit, see what the output state is. So we expect this to give us a quantum state at the output. Now, the output here is admittedly confusing to look at. So let me just be clear about what it's saying. Here we have a 4-dimensional vector, and each element in the vector is a complex number. So it has a real and an imaginary part. The first element of the vector is this number right here. So it has a real part, 0.707 blah, 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 which as a reminder is just 1 over root 2. So real part 1 over root 2, imaginary part 0. The second element has a real part of 0, which for various reasons extends all the way through this space. That's just a single 0. 0 real and 0 imaginary. So that whole element is just 0. Same deal with the third element, 0 real part, 0 imaginary part. And then the fourth element, again, has root 2 as the real part and 0 as the imaginary part. So this is what we're expecting because, again, the first element represents the 0, 0 state and the fourth element represents the 1, 1 state. We're expecting to get that first Bell state, which is 0, 0 plus 1, 1. And all looks good so far. So that's one way to look at your output from your simulation. Another way is to look at a histogram, essentially. So in the circuit composer, in the sort of bottom left of the screen, we saw the measurement probabilities of our various outcomes. In Qiskit, again, using our result object, we can use result.getCounts. And that's going to give us a little dictionary here that tells us 0, 0 has a 0.5% chance of being observed. 1, 1 has a 0.5 probability of being observed. And then the other ones are never going to get observed in theory, right? So that's a pretty simple output. You might start to notice that there's a pattern here. Every time we are working with this result object, it's usually going to be some variant of get blank, right? So get your state vector, get counts. All of those are different ways you can start to interpret your results. Okay, and then the final thing we're going to do is actually plot a histogram with these counts. So again, that was just our variable that we created up here. Actually, I think I forgot to run this cell. So let me make sure I do that. Okay, there we go. Run that, and now I can go ahead and plot a histogram. And we see exactly what we saw in the circuit composer, which is 50% 0, 0, 50% 1, 1. There's a bunch of different ways to visualize the answer to your simulation. As we saw in the circuit composer, there's everything from these histograms to up to these, like the Q sphere and other complex representations. There's a lot more where this came from, but these are just some of the basic ways you can start to visualize the output of your circuit. So just to do a quick overview of what we've done, because I know there was a lot of code and I started to go a bit faster at the end for sure. Just to do a quick overview of what we've done though. We started off by, if I go all the way back up, defining a circuit, right? And we think, based on our theory, that this circuit should give us the first Bell state, which is 0, 0 plus 1, 1. And we saved this circuit in a variable called circ_bell. Now, we essentially want to use Qiskit to verify that we have indeed created the first Bell state. So in order to do that, we're going to use one of the simulators in AIR called the state vector simulator. And what that does is it computes the state vector that is the output of some circuit. So we've given it our circuit. We want to use the state vector simulator. So we use AIR, we get that backend. And then the magic command we use to run everything, to run our simulation, is execute. So execute takes our circuit that we want to simulate, plus, I guess another way to think of the backend is sort of what type of simulation you want to run. So the type of simulation here is we want to get the output state vector. So we give that to it. Now, once our job runs, we can get the result by using job.result. And then we use this result variable to look at the state vector, to look at the counts of our various output states. All that kind of stuff is result.get underscore, and then whatever you want to get. So get the state vector or get the counts. And that's how you can start to figure out the results of your experiment. Okay, so a few quick key takeaways. This is usually what we have at the very end of our slideshow. I think I already pretty much went over everything here. I guess the only one I didn't really go over again is the way you can add single qubit gates or multi-qubit gates is by using this circuit name dot gate name and then where you want to apply the gate. That's always going to be the way it works in Qiskit. A bit of additional reading is provided at the end here, which you can look into if you want. And that is the end of what I have prepared for today. So I do apologize for going over time. I sort of lost track of time, to be honest, in the middle of that. But let me go ahead and pop up the post-Zoom feedback again to see how you all are feeling now. And in the meantime, I will go back to the questions in the chat. Okay, so there was, okay. There are a few direct messages. I just want to make sure I end up getting to those. Okay. So I guess, yeah, as you fill out the post-lab Zoom feedback, feel free to drop off after this. I guess I should have mentioned, there's actually no optional content for this lab. So we're done the required content. I'm just going to stick around for a while and answer some questions. We can have some more fun with Qiskit and trying out some more complicated circuits. But all of that, I think, is good just review to sort of learn how this framework works. At the end of the day, the best way to learn Qiskit is just to practice, right? Type things out yourself, open up this notebook. One thing that you can try is just go to this notebook and delete all of the code segments, right? Delete all of the code blocks and just see if you can come up with all of that code on your own again, just to start getting the muscle memory of typing these things out. Okay, so one person asked a great question here. I'm just going to throw some of my answers to these questions at the bottom of this notebook. So I'm going to launch into questions now, I guess, just to be clear. So if you need to head out, feel free to do so. There's no optional content. So all I'm going to be doing from here on out is answering questions. So if you do need to head out, have a great week. And if you are going to stay behind, let's go ahead and answer some of your questions. Okay, so one person asks, how do you, if you wanted to, how do you initialize two different qubit states? So basically, if you had two qubits and instead of wanting them to be in the 0, 0 state at first, you wanted them to be in the 0, 1 state, for example. Great question. And there are a couple of ways to achieve this. The way that I'm going to recommend for us, at least for now, is to use the tools that we're already familiar with. So what you can do is you can start off with a circuit. So I'll just call this a 0, 1 or init 0, 1 circ, just for initializing 0, 1. So I'm going to create a quantum circuit with 2 qubits, right? And actually, one thing that I kind of like to do, just as a general practice, I guess, as I'm doing these things, I will put a line at the bottom of my code cell here that draws my circuit. So I can draw it as I'm working on it. So in this case, I'll do init 0, 1 circ.draw. And again, we'll use matplotlib. So if I go ahead and run this code, I'll just click the run button again. We'll see here that we get 2 blank qubits. As we know, of course, these qubits are initialized to ket 0. So if you wanted to initialize them instead to ket 1, honestly, what I would recommend is just add gates to your circuit until you get the states that you want. So if we wanted to be in the 0, 1 state, how do we get there? Well, we just need to apply an X gate to qubit 1. So in order to do that, I do my circuit name, init 0, 1 circ, dot, and then the name of the gate. So this is going to be an X gate. And then as an argument, I'm going to give it which qubit, 0 or 1, I want to apply it to. So in this case, I want to apply it to qubit 1. If I go ahead and run my code again, I'll get my picture to update. So here we can see there's now an X gate on the qubit 1. And now the state at the end of this circuit will be 0, 1. So if you wanted to see what happens to a CNOT gate, if you run it on 0, 1, you could add a CNOT gate after this, or any other type of circuit. So there are other ways of doing initialization, but this is one way that we already know how to do. Okay, so somebody asked about the homework this week. Should the state vector simulator be used? I believe so, unless otherwise specified. Remember, though, when you're selecting simulators, if the goal is to compute your output state vector, then the state vector simulator is what you want. If the goal is to compute the unitary, for example, then you would want the unitary simulator. So it kind of depends what exactly you want to get out of your simulation. Okay, so let me see. Somebody asked the question about state vectors. So let me go back up to that part of the notebook here. Okay. So they ask, when you were working with state vectors, how did you decide that this expression, this big, ugly expression for psi, corresponds to this state vector? So the simple answer here is that our state vectors are always written with the computational basis elements in counting order. So again, if you think back to our binary lessons, we always start with 0, 0, 0, 1, 1, 0, 1, 1, because that's just counting up in binary, right? In binary, that is 0, 1, 2, 3. So our state vector is always in counting order when you look at the binary representations of your qubit states. So here, we started off with Dirac notation telling us what each of these coefficients referred to. In a state vector, you just need to remember that you have to order them in that counting order for it to make sense. I hope that helped. Quick question here. Somebody asked, is the job, this little job thing that I typed here, is that a variable or a keyword? It's only a variable. So just like any other variable, I could call this whatever I want. I could call it my job. As long as you're consistent with what you call it throughout your notebook, everything should work. Oh yeah, so people are saying that apparently in the notebook that you got, I think it was this line originally that had something like this. It said print state vel, then it had compact equals true toward the end of the print statement. That was a typo in our original document. I thought it got fixed, apparently not. You're right, compact equals true does not work. Don't worry about it, just delete it. It'll give you an error if you try and run it like that. So it should just be print state vel like this. Okay, so somebody asks, when executing with the QASM simulator and no measurement, a 2-qubit equal superposition produces 0, 0 with 100% probability. On the other hand, adding all measurements gives the superpositions with 25% probabilities. What is the QASM simulator simulating when no measurements are applied? Yeah, that's actually a really good question. To be honest with you, I'm not sure. So according to my understanding, I would have guessed that trying to run a circuit with no measurement. So for example, here, when we defined our Bell circuit, you might notice that we just applied these gates. We don't have any measurements here, right? Last week, when we used the circuit composer, we ran into an error unless we put the measurements on each qubit. I would have guessed that the QASM simulator in Qiskit would give you an error if you tried to execute a circuit like this. If it doesn't, I'm honestly not sure what it's doing. It would only make sense to me to simulate something with measurements using the QASM simulator. So I'm not sure is the short answer. Yeah, sorry about everybody running into that compact equals true thing. Yeah, so somebody asks, can you give an example of why it's important to know the probability of, for example, getting 0, 0 or 0, 1 as a result. So this is in reference to, once we created our circuit, once we select our backend, we execute our job, one of the results that we get is this counts thing, right? Which tells us the probability of getting any one answer. Now, the reason this is important is because in quantum computing generally, when you run an algorithm to solve a problem, the answer to your problem is usually encoded in the probabilities. So for example, if we were doing the Grover search algorithm, right? So we haven't learned Grover search yet, don't worry. But the way that Grover search works on a high level is you'll have tons of qubits, right? You might have 100 different qubits. And every bit string, every combination of zeros and ones indicates a certain position on a list. And you want your quantum circuit to figure out whether a particular element in that list matches something you want. So as an example, I could try looking through an address book for a particular person to see if the person is in the address book. When you run your circuit, what you'll find is that the index or the particular bit string pointing to the person you want has probability close to 100%, or at least has higher probability than the rest. So I guess that's kind of a convoluted answer, but the short answer to that is this counts object that you see here is usually how you get the answer to some quantum algorithm that you're executing, is by how probable any of your bit strings are. Oh yeah, this is a good question too. So somebody asks, how come we don't have to call print when we plot our histogram? And you might notice actually, there's a couple of instances, well, maybe not as many as I thought. Okay, well, there's a couple of instances where we don't need to call print, right? So one example that I can think of is when we do circ.draw. There's no print statement here, but it still draws something in our notebook. The short answer to that is that Jupyter notebooks have this feature where they will by default print whatever comes last in your cell. So just as an example, previously we had our counts object, right? So we defined a variable called counts. We get our counts from our result, and then we called an explicit print here. If I just do a cell that has counts in it, just like this, nothing else, and I click run, it's going to by default print whatever the last statement is in our box, or in our cell, sorry. So a lot of the times you'll see us just omit the print statement, and the Jupyter notebook will just automatically print whatever comes last in your code block. So yeah, it's a really good observation. Okay. So somebody, yeah, okay. So I think that the notebook that you all have is a not updated version, unfortunately, compared to what I'm looking at. So the other distinction that somebody pointed out is apparently in this line here, you had result.getStateVector, and then you had circ_vel as an argument being passed here. That is okay, that works, but it's not necessary. So the way that I've done it here without passing any argument to the state vector function is totally fine. And in fact, in my opinion, kind of recommended, just it's simpler, right? The reason that you sometimes need to pass an argument in here is because you can define a job. So remember up here when we did our job equals execute, you can define a job to do multiple things at once. So there is a way to pass in multiple circuits that you want executed. And then when you get the state vector from your results, you would have to tell it which circuit's result you want to see. Now here, we only had one circuit in our job, so it already knows which circuit we're referring to. 90% of the time, honestly, this is how I use it as well. My jobs will only have one circuit in it, and so we don't need to specify any further arguments with the get state vector call. Okay, so somebody asks, is there a way to save local values in the notebook? Yeah, so there's a couple of ways that you can save these notebooks, and you can pick whichever one works for you. The first thing that I will mention is if you just, if you're on the IBM Quantum Experience, I'm in this notebook right now, and I just close it, right? and I log out of my account and I come back later and I reopen this notebook, everything that you ran and all of the outputs should be saved. So once this, I'll give this just a chance to load. If I scroll down all the way to the bottom, for example, you can see all of the examples that I added here are still written down. So when you close your notebook, it is automatically going to save all of the outputs. If you want something that does not require an internet connection, though, if you want sort of like a local copy of the notebook, you can go to File up here. I think it's File, Download As. And then if you download it as HTML, you'll get a local version of this notebook that you can open without an internet connection. So that will, like in a more real sense, it'll save everything to your local computer in case you wanted to look at it without internet. The only thing I'll note there is that if you save it without internet, it won't be interactive anymore. So you can no longer change the code and run the code, but it does save all of what you see on your screen. Okay, so somebody asked me to discuss Bell states a little bit more. So I can go back up to that section. I'm not exactly sure what else I would discuss on this. I honestly think that, Bell states, it's something we're introducing you to here just because we're creating a circuit that does a Bell state. For the time being, though, I would say just like, you can memorize these definitions, or you don't even have to memorize, just keep a reference handy so that you know what we mean when we're talking about the various Bell states. And all you really need to know is these definitions. We'll get into stuff later on in the course about how you create, the second, third, and fourth Bell states, why they are important. They are, there's a reason that they're named, right? They are important states, but we haven't really talked enough about multi-qubit systems yet to have a good understanding of why. So when we get to multi-qubit systems, which is coming up fairly soon, I think in the next couple of weeks, then we'll definitely revisit the Bell states, and hopefully you'll get more on them then. Okay, yeah, the compact equals true thing, like I said, that was just a typo. It does not work. It doesn't work in any world, so just get rid of it. Forget it ever happened. Hi, okay, so somebody says, could you please share how we can change the probability of the states using the circuit? Yeah, so let's go down and look at our get counts again. So here, again, we're looking at the probabilities of our various outputs, right? Now, one way that I can modify these probabilities a bit is, well, for example, I could apply a Hadamard gate to the first qubit, right? So if I apply a Hadamard gate to the first qubit, we should get every single possible computational basis state as possible outcomes. So let's go ahead and give that a try. This will also be a good review for just the whole sequence of defining a circuit, running it with a simulator, seeing your results. So I'll go back up to our circuit here, and I'll just make one change. I'm going to add a Hadamard gate, and I don't know, maybe I'll add it on the second qubit this time. So again, circuit name dot gate name, and then you just need to tell it which qubit you want your gate applied to. Go ahead and click run just to make sure that that looks as we want it to. So yes, it does. We have a Hadamard, CNOT, and then Hadamard on Q1. Okay, so let's go down and do the simulation. So I'll go ahead and I'll just call this new job for clarity. So our new job, we're going to execute that Bell state again. Well, we'll execute our circuit. It's not going to be the Bell state anymore, using the state vector simulator backend still. So I will click that, goes off and runs. Okay, and now here we will get the result. We'll run that. Okay, and then next up we do the get counts. We'll run that. Oh, actually, okay, this is a good teaching moment. Okay, so one thing that I did not talk very much about in the lab is just the fact that these jobs can take a little while to execute, right? So one thing that you can do to check whether your job has executed or not is you can use job.status. So again, before we had job.result to get the results of your circuit simulation. Here, we're going to use job.status. So if I run this, again, I'm using the trick here that if you just put something in the cell with no print statement, the last item is going to be printed. So if I click run, here we see that now our job is done. Now, if I had been a little bit faster on that, we probably would have seen that the job was executing or verifying or something like that. And we just have to wait a little bit. So if you see something that is not done, give it another 10 seconds. And then after 10 seconds, you can run the cell again, and then just keep doing that until you get done as the result. That's assuming that there's no errors. You might get an error message here. If that happens, maybe you can fix it, or maybe you can post on Piazza. Okay, so now that we know our job is done, I'm going to get my result again. Oh, actually, I know what went wrong. Sorry. Yeah, we want to get the result of our new job, because I changed the variable name here. So again, we'll do result equals new job dot result. Cool. And then I will go and get my counts, and we should see this updated. There we go. So now you can see that the probabilities have changed. We now have a 1/4 chance of seeing any of the computational basis states, which again, if you go up to this circuit and you work this out logically, kind of like we did at the end of the lab last week, you would see the same result, that you should get a 1/4 chance of any of the possible basis states. Okay, so somebody asks, get counts doesn't hold other result metadata. How do we get the other qubit data? Great question. So you are correct that this counts object doesn't tell you everything about your result, right? And in particular, it tells you the probabilities. It doesn't tell you the relative phases. So I know that phase is a confusing concept for everyone in quantum computing, but we've talked a little bit about phase. No worries if this doesn't make sense, but generally speaking, looking at the probabilities of your simulation does not give you any information about the phase. If you wanted to see the phase, one way you could do that is by looking at the state vector. So the state vector, as a reminder, is going to give you a full complex number for every single computational basis element. And that gives you probability information if you took the modulus squared of this, but it also gives you phase information if you look at the angle of this complex number. So hopefully that answers that question. Somebody says, we still need clarification on the Bell states with phi and psi. Sorry about that. So yeah, let me clarify. So just to say it out loud, this character here, the top one is phi, P-H-Y. The one down here is psi, P-S-Y, or sorry, P-S-I. So yeah, when I've been saying, phi plus is the first one, psi plus would be the third Bell state. And they always just have these definitions. Okay, so somebody asks, for a 2-qubit circuit, how can we find which bit should be rotated around which axis? So I'm not exactly sure what that means. I guess if you're asking can we rotate around different axes rather than just a Hadamard gate or the X gate, for example? Yes. So I don't know off the top of my head what those gates are called. I think they would just be RX, RY, and RZ gates. You can actually just go ahead and try it. So if I do circ bell dot maybe RX, now an RX gate, I'm going to have to tell it which qubit. I'm also going to have to tell it the angle. Yeah, so I'm not exactly sure what the syntax is supposed to look like here. So this might give me an error. Oh, no, it doesn't. Okay, cool. Okay, I see. So yeah, I guess for an RX gate, the way that this works is you would pass the angle of rotation as the first argument, and then the qubit you want to apply it to as the second argument. So I just kind of guessed and checked there. If you wanted to be more rigorous about this, if you go all the way down to the further reading and resources, what would be a good one? Well, I guess probably any of these would have a list of gates, but if I just go to the list of Qiskit resources, well, maybe it is the textbook would be the best one. Yeah, so here, if we go to the single qubit gate section, here, yes, rotation gates, X gate, yeah. I'm not exactly sure. As you can tell, I'm not super familiar with the documentation here, but this would give you a similar sort of introduction to all of the stuff that we talked about. Yeah, I don't know. There would be a reference somewhere that tells you how to do all the different gates. I'm not exactly sure where it is at this moment, but I'm sure it exists. Okay, so I addressed the issue of saving notebooks. What's my favorite gate, and tell us why? Huh. I mean, I guess just because it's what I spend all of my days researching, I have become intimately familiar with the Control Z gate. It's not particularly interesting, but it is sort of the basic building block of entanglement. So it turns out to be a pretty important gate when you are developing new types of quantum computers to figure out good ways of doing a Control Z gate. Yeah, so I guess that's probably my favorite gate. So somebody asked if I could talk about RY gates. I think that's a bit too much of a digression for this lab, but I did talk about the rotation gates, I think 2 labs ago. So actually, maybe I'll include that in a follow-up, or in my announcement follow-up, I'll include a link to that lab. Okay, so somebody asks, can I get the previous code once I deleted the code in the notebooks? That's a good question. I am not sure. I mean, I'm sure there's, you can use undo functions. I don't know if there's a way to sort of get history back in your notebook. But what you can always do for this course anyway is just go ahead and re-download the notebook, right? If you go back to Canvas, re-download the notebook, it'll have all of the code there again. Okay, so somebody asks, is the Hadamard and CNOT in the circuit an entanglement or superposition operation? Great question. Exactly how you would determine that is not something we've taught yet. So I guess I'll just give a short answer because I don't think I don't really want to get into exactly how you determine whether things are entangled. The short answer though is a Hadamard gate does a superposition. As we can see, it goes from 0 to a superposition. It goes from 1 to a different superposition. The CNOT gate is an entangling operation. So what makes the Bell state an entangled state in this particular circuit is the CNOT gate. As a general tip though, single qubit gates can never entangle, right? Because entanglement is a property that exists between 2 or more qubits. So single qubit gates are never going to entangle things. Okay, so somebody says this week's quiz is incorrect. I'm not exactly sure what that is referring to. Yeah. Oh, I remember. I was supposed to go over the Canvas attendance quiz questions. So maybe let me do that fairly quickly. Okay. So if it's okay, I'm not going to switch back screens. I'll just read the questions. So again, it was, are the following statements true or false? Quantum states can be represented by vectors whose direction gives us information about the probabilities of different measurement results. The answer to this should be true. So quantum states are vectors. The direction of the quantum state is kind of another way of saying, how much of the coefficient is on the 0 versus the 1. Right? And so that tells us the probabilities of being in those states. The second question was, when a quantum state is measured, it can change as a result of the measurement. Yes, absolutely. So that's true as well. That is one of the things that makes quantum computing very different than classical computing, is that the very act of measuring your system changes the state of that system. Next one was, quantum states always stay the same. They never change. That's false. Quantum states do change when we apply gates to them, right? So if we apply a Hadamard gate, it's going to change a ket 0 into a superposition state, as an example. And then fourth question, quantum states can be represented by a single number, a scalar, and a measurement of the state gives us that number as the result. So this, a little bit of a trickier question. The answer to this is false. The best explanation I think I can give is if you think about a state vector, right? We always use a state vector to represent a particular quantum state. And a state vector is not just a single scalar number, it's actually two scalars, right? Two complex numbers that you need to represent a quantum state. So the answer should have been true, true, false, false. Okay, so back to questions in the chat. Somebody asks, what do you mean by simulators? Are we using quantum mechanics computing model on classical hardware to get an ideal answer and not on a real quantum computer, and the noise is just fake? Exactly. So whenever we're talking about simulators, and by the way, everything in AIR, this AER package that I talked about, everything in AIR is a simulator. So as long as we're using AIR, we're not running on real quantum computers. And all of the simulators in AIR are just going to use classical computing techniques to try and emulate what a quantum computer does. So as I described a little bit last week, the best way to think about that is IBM has taught their classical computers how to do all of the linear algebra that we've taught you, right? And so now their simulators can go away with this quantum circuit. They will multiply a bunch of matrices and vectors together, and that's how they get their answers. Yeah, so somebody sent the question about QASM simulator with no measurements again. Again, I'm not sure what's going on there. Perhaps I can try and look into it actually, and if I find anything interesting, I'll include it in the announcement. Oh, okay, so somebody asked a question about, let's see, the state vector. Oops, where's our state vector? Here. And they asked, how did we figure out these coefficients? Just to be clear here, this ket psi is just an example. It doesn't have any significance in the context of the rest of the lab. So we just wrote this example to demonstrate the equivalence between the bracket notation and the state vector notation. So don't worry about what this state means or anything like that. It's just a random example. Will we get the updated notebook with additional content after the lab? Sure. Yeah, I will attach my updated notebook to the announcement when I send that out. Okay. Attendance code. So somebody says it's in the homework. What Bell state does a given circuit create? Oh, I see. And then they ask, oh, interesting. Okay, so I guess there's a homework question that says something along the lines of what Bell state is created by a certain circuit. Is it phi plus, phi minus, psi plus, psi minus? I'm not sure what lecture that would be, to be honest. I feel like that's a pretty tough question given what we've taught so far. I think my best recommendation for that would actually, and this is just from what I know, would be what I went over in this lab at the questions at the very beginning on how the CNOT, or actually, no, you know what? A better one would be the one from last week. So why don't, I'll attach a link in my announcement to that part of last week's lab where I explained how the Bell state preparation circuit works. Because I did go through how the Hadamard gate, like what the Hadamard gate does, what the CNOT gate does, and how you come up with that answer of the first Bell state in a fair amount of detail. So that's the one that I'm familiar with. I'm not sure if they went over it in lectures, but I will include a link to that when I send out my announcement. Okay, so yeah, apparently there's a homework question that asks you to use an RY gate. So we will get that circuit. I'm confused about that. So without looking at the homework question, I'm not sure I can say much more about how to do this. But when I send out the announcement, again, I will link to both my discussion on the RY gate, as well as my discussion on how the Bell states are formed. If both of those things still don't help you, definitely feel free to post on Piazza, right? I would say that's always the backup option. If you still can't figure out the homework, post on Piazza or go to one of the Friday review sessions as well. Okay, so somebody asks, can you go over the state vector simulator vector again? Yes, absolutely, because I think this is kind of confusing as well. So down here in this cell, we printed out the state vector from our state vector simulator, right? Now, just to sort of drive home what this is showing us, this is a vector, 4-dimensional vector, but just due to how Python prints things, it's printing it horizontally instead of vertically. So what we saw earlier was a state vector that looks like this, right? Where ket00 was the top, ket01, ket10, ket11. When we print out our state vector using getStateVector, it's the exact same thing, but the whole vector is horizontal instead of vertical. So try to keep this picture in your mind, right? Vertical counting up in binary. When we print our state vector, it's the same idea, but now we're going from left to right. So the leftmost number, which is a real and imaginary component, is ket00. The second one is ket01. The third one is ket10, and the fourth one is ket11, right? Just the same as the vertical vector, but now it's written horizontally. Excuse me. The only other thing I'll point out here is the spacing is quite confusing, right? Like the huge space here kind of makes it look like all of this is the same number. It's not. You really just have to read it as like real, imaginary, then the number ends. 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 I agree the spacing sucks. It's the way that it works though. Okay. So somebody asked about the job, new job variables. Again, those are just variable names. So I can change this. There's nothing special about this. I could call it Corbin job, right? Just a variable name. As long as you're consistent with it throughout your code, it doesn't matter what you call it. So yeah, for the people asking about the RY gate, again, I will link to that discussion 2 weeks ago where we talked about how the RY gate affects qubits on the block sphere. So hopefully that will help. Is there a way to know the default arguments to pass to a function or the syntax for that? So the way that I would recommend is just keep copies of these notebooks, right? Because in the notebooks, we're going to introduce each function to you by explaining very clearly what inputs and outputs it has. Now, there is also documentation online that Qiskit provides, which provides the same information in way more detail. So the reason we're not just giving that to you is because it can be quite overwhelming when you're just getting started. So for now, I would recommend just keeping these notebooks, and hopefully we do a good job of explaining what all the arguments are. Okay. So somebody asks, can I get all the resources even after the course is completed? I'm not sure about that. It's more of an admin question, I guess. I'm sure that if you just emailed us and said you were a past student, though, we would hook you up with the resources, I think. So somebody asks, any books or articles which shows us how we can effectively create quantum circuits from basic classical logic gates, for example, a half adder or a full adder? Not off the top of my head. Usually we don't have much reason to create classical circuits in quantum computers because a classical circuit, should be faster most of the time, right? Actually, I guess one person is saying they should show it in the homework session. I'm not sure, but I don't know any resources off the top of my head, personally. Cool, okay. So one person says, after job execution, the Hadamard, yeah, okay. So the Hadamard is represented as these different circuit gates being applied with RZ and SX and so on. My best guess for that would be that it's transpiling your circuit. So I talked a little bit about transpiling last week. I will link to that discussion as well in my follow-up announcement, because I think I already talked as much as I would want to talk about it back then. Okay, so I'm going to grab a quick drink of water, but I think I am at the end of the questions. If I didn't answer your question and you want me to see it again, just copy paste it again in the chat, and then I'll take a look. So any other questions I did not get to? I know there's a lot of questions, so I do apologize if I missed yours. It's nothing personal. Just let me know if I missed something. Cool. Okay. So looks like that's pretty much it. I guess I'll wrap things up there then. So thank you everyone for staying out right until the end. Yeah, I think I'll wrap things up here, but if you do have any more questions that come up, feel free to post on Piazza and we'll be sure to get to them there. So thank you everyone. We'll see you again next week. Bye.